here is a vernier scale. So vernier scale can slide over the main scale, dear children. Can you identify this device? Can you? Yes, I have one more device. What is this device actually? Yes, it is nothing more but so this is a diagrammatic representation of the simple pendulum. Yes, this is how actually simple pendulum seems to be. Children, here is a simple. Hello dear children, in today's class we are going to discuss the entire chapter of measurements and experimentation. Dear children, previously we had uploaded the same chapter but a unit wise we uploaded. So there each and every topic was discussed in detail. So links will be given in the description, just go through those videos if you need a in detail discussion. In today's class also we are going to discuss all the concepts but in a shortcut, so that this video is very useful to you if you want to revise the entire chapter in a less time. Dear children, we know that this chapter 1 is consisting of 3 units. In a unit A, basic concepts of measurement and the units of mass, length, time is going to be discussed. Whereas in a unit B, we are going to talk about the, in detail discussion we will be having about the units of a length or a measurements of a length and how are going to measure, by using a vernier calipers and a screw gauge. In a unit C, we will be having a discussion about the simple pendulum. There we will be talking about the terms related to the simple pendulum, and even we will see how can we calculate the acceleration due to gravity by using a simple pendulum. So these are the concepts which we are going to discuss in today's session. We are going to cover all concepts related to the chapter 1, that is measurements and experimentation. So now children, here a few important or we can say the topics what we should cover, what we should learn about. It's a beginning. First we should know about the physical quantity, measurement, unit, characteristics of the unit, and guidelines to write the units. So first dear children, let us try to understand about the physical quantity. Physical quantity. So let us try to understand about first physical quantity. So dear children, if all of a sudden I will ask you one question, that do you all love your parents? Of course you can you can say that, sir, what is this question? You may feel that, sir, of course we all love our parents, right? Yes, every one of us will love our parents. That has to be, that's very important. Okay, but someone will ask you a question, how much do you love your parents? Can we express that? Of course, no, we cannot express. Because that love is related to our heart. It is a feeling. Like love, dear children, like, dislike, irritation, frustration, hungry, angry. It's a madness. These all are the feelings, which we cannot measure. But if I ask you a question, what is your height? Are you able to tell you that answer? Yes, of course you can tell, sir, 155 centimeters, 160 centimeters. Obviously we can say that. What about the weight? Yes, we also can measure the weight. Now, you are sitting in a room. Dear children, can you measure the area of that room? Yes, of course we can measure. Can you also measure the volume of that room where you are sitting? Yes, we can measure. So like this, if you can see mass, weight, time, temperature, work, power, pressure, density, force, momentum, these all are the quantities which can be measured. So if you can see you can see the entire universe, dear children. So quantities, they are classified into 2 categories. Few quantities, say the feelings which cannot be measured. But whereas the quantities like work, power, energy, pressure, momentum, force, acceleration, velocity, speed, these all are measurable. So what actually physical quantities? The measurable quantities are called physical quantities. I repeat once again. What is physical quantity? The measurable quantity is called physical quantity. Example, yes, till now I told you. What is that? Displacement, acceleration, velocity, force, work, power. This all comes under physical quantity only. Is the point clear? Yes. And the next one more term is what actually? Measurement. Measurement. So dear children, when we go to a shop, to buy, let us say rice, Okay, so if you want some 10 kg, 5 kg, 2 kg, so that rice will be there in a bag. The rice, okay, in this rice will be there in a bag, and to measure this they will use a weight, right? Yes, it might be, let us say it's a 1 kg weight. Okay, so this is known one, right? It is a known one, known standard quantity. It is known standard quantity. So whatever we are going to measure is actually unknown one initially, unknown one. So what we have to do, what the person will do, yes, he will take the rice, okay, he will take the rice with the help of this 1 kg. Okay, if you want a 10 kg, 10 times he will measure, 10 times he will give you. If you want 5 kg, 5 times of this weight he will give you. Means here some process is going, right? It's a process. Here in this process, what are we doing? We are comparing a known standard quantity, or else we are comparing unknown quantity with a known standard quantity. This process only we can call it as a measurement. So children, what is a measurement? The process of comparison of unknown quantity with a known standard quantity is called measurement. Is the point clear? Yes. Now dear children, any physical quantity if you can take, then how can we express a physical quantity? Dear children, physical quantity is expressed in terms of two parameters. Look at here. So before going to learn about the parameters in which a physical quantity can be expressed, we need to learn about one more thing also. What is that here? We should learn about the unit. So children, here this rice whatever we are going to buy is actually unknown one, but we are comparing with what? 1 kg weight. This 1 kg weight is a unit. 1 kg weight is a unit. So unit means it must be known and it must be a standard quantity. Is the point clear? So what is the unit, dear children? Here the known standard quantity which is used to measure the unknown quantity of same nature. Here why are we using the same nature? For suppose if you can take a second, okay, second also known standard quantity only, but can we use this second to measure the rice? Can we measure the rice? No, we cannot use. Why? Nature is different. You are purchasing rice in terms of it is a mass, second represent time, so time and a mass both are different. So whenever you are comparing unknown quantity with a known standard quantity, make sure that both must be of same nature. This point is very important. So what is unit, dear children? Unit is a known standard quantity which is used to measure the unknown quantity of same nature is called unit. Okay, fine. Then how can we select a unit? What are the characteristics of the unit? So children, here characteristic or a choice of unit we can say that, or else we also can use the characteristics of what? Unit. So what kind of quantity should be taken as a unit? Okay, for suppose the first one, dear children. So you go to a shop, for example morning, you purchased a 1 kg rice, you got this much. When you go to the evening, you got only this much rice. Do you accept? No. Just we go to the shop person and will question, and if the person say that yes sir, it was a morning, so that you get a more quantity, whereas the evening you won't get a more quantity, you'll get a less quantity, means do you accept? No. 1 kg weight means either it's morning or evening should be of same quantity. And let us take one more example. For example, you are purchasing a rice in Hyderabad. Let us say that you got this much quantity. This much quantity you got. You go to some X village, there you purchase 1 kg rice. There you got this much quantity. Do you agree that comparison? No, we don't agree. And if you definitely question a person who is selling in Hyderabad, and if the person says that yes sir, village mein you will get village mein zyada milta, but Hyderabad the city you won't get a much quantity. Do you accept? No. Morning or evening or Hyderabad, some X place or Delhi or wherever it is, so that quantity whatever we are using as a unit, it should not change with the space and time. So it should be constant throughout the universe. Okay na? So it should not change. It should not change with space and time. it should not change with the space and time. And second one is that, for example, 1 kg weight is there. If a person is used to measure the some rice or dals, whatever. If it is lost, but he should be able to purchase, right? It's to purchase, it should be available. To available what actually? It should be reproduced. So it's a very important thing that any quantity, if you are using it as a unit, means it must be reproducible. It must be reproducible. Very, very important. And 1 kg weight, if you can talk about the one, see, you may get wondered, sir, why are you talking about all the way 1 kg weight? Because units, we are very familiar with that. Other than this also, you can take anything. 1 meter you can take, anything you can take. Okay, fine. And third one, 1 kg weight, dear children. So it can be carried easily or not? Yes, of course, you are purchasing. But to carry that, from that shop to some X place, if you need 10 person, 15 persons, 100 persons to carry that, no, do you accept that? No. So the whatever the quantity which you are using as a unit, it should be convenient in size so that it can be carried from one place to another place easily. So that unit should be convenient in size. Convenient in size. And the fourth one is that it should be well defined. It should be well defined without any ambiguity. Without any ambiguity. Ambiguity means what? Doubt actually. So when I say 1 kg weight, yes, you all will think, you all will get information that yes, 1 kg is equal to 1000 grams. 1 meter, when I say that yes, 1 meter is nothing but 100 centimeters. So wherever you can go in the world, children, so it must be well defined without any doubt, that is without any ambiguity. So these are the characteristics of the unit. What is unit, children? The known standard quantity which is used to measure the unknown quantity of same nature is called what? Unit. And these are the characteristics. Now let us come, how can we express the physical quantity? So as I told you that any physical quantity can be expressed in terms of two parameters. So for that, let us take one example. Okay, so let us say we measure the height of a one person and we record it like this. So height is equal to I can say it is 100 centimeters. Okay, here height is what? Length. Length is nothing but what? Physical quantity. So it is a physical quantity, and 100 is a numerical value, and a centimeter is a unit. Centimeter is a unit. So now can we express like this? Physical quantity is equal to numerical value into unit. Yes, of course we can express. So which means what? Physical quantity can be expressed in terms of two parameters, that is numerical value and it's a unit. Okay, so what is a unit? Just we discussed. So it is a known standard quantity of a same nature. Centimeter, it is a length in nature. Height, length we are using. But what does this 100 will tell you? So this 100 will tell you, for suppose dear children, let us say this is some height something. Okay, we want to measure this length. We want to measure this length actually. So now let us say that it is from here to here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let us see that 10. I mean what? Each one is 1 centimeter. So now it is contained how many centimeters? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I can say that it is a 10 centimeters. So this numerical value is telling that this unit centimeter is contained 10 times in that particular object, in that particular length actually. So that physical quantity contains centimeter. How many times? 10 times it contains. That information we get from this numeric value. Okay, fine. So now let us see here. This can be, can I write like this, dear children? So as PQ is equal to, that is physical quantity is equal to numerical value to unit. Can I write like this? N1 U1 is equal to N2 U2. Then you may get one doubt. Sir, what is this N1 U1 or N2 N2? Let me give you. So let us take this height only. So here height is equal to 100 centimeters. Can I write like this? Height is equal to 100 centimeters. So or else I can say 1 meter. 1 meter. So don't you think that 100 centimeter is equal to 1 meter? Yes, of course it is equal. Okay, or else if you get 160 centimeter, anything is okay, anything is okay. So here, because you are changing the unit, do you think that the physical quantity will change? No, physical quantity remains constant, whatever may be the system of unit you use. So height both are same. Or can I write like this? 100 centimeter is equal to 1 meter. Yes, we can write. So this 100 is nothing but N1, this centimeter is a unit 1, and this 1 is a N2, and this meter is a U2. So what I mean to say is that here, when you change the system of units, the numeric value will change. This is a very important point to be noted. Dear children, when you change the system of units, the numerical value will change. Is the point clear? Fine. So this is about actually a physical quantity, a measurement, unit, characteristics, and the parameters in which physical quantity can be expressed. Okay, fine. Now let us take a physical quantity. Let us discuss in detail physical quantity types and the units and the types, and even we also can see the system of units. Okay, fine. So children, now if you can take a physical quantity. So dear children, so we have two types of physical quantities. So the first one is fundamental, not mental, okay, no, fundamental or basic quantities. The second one is the derived quantities. So dear children, what are fundamental quantities? The quantities which do not depend on any other physical quantities, or the quantities which cannot be derived from any other quantities are called fundamental quantities. So whereas a derived quantity means what here? The quantities which can be derived from, I can say, fundamental quantities or basic quantities are called derived quantities. So children, here we'll discuss fundamental. First we'll try to discuss about the fundamental, and and as we learned that so to express any quantity, definitely units must be used, right? Okay na? So here the units which we use to express the fundamental quantities we can call it as a fundamental or basic units, and whereas these quantities are expressed in terms of derived units. Okay. Now what are fundamental units and basic units, dear children? The units which cannot be derived from any other units are called fundamental or basic units. What about derived units? The units which can be derived from a fundamental units or basic units or derived units. Okay. So here, to measure the physical quantities, dear children, actually we have three systems, right? Three systems. What are those? We have FPS system. Sorry, first one is CGS system, French system, and FPS, British system, and MKS, metric system we have. So this first one is actually what it is a length. First one is a length, and the second one is a mass. So third one gives actually time. So in a CGS system, length is measured in terms of centimeters. In FPS, foot, MKS, meter. Whereas in a CGS system, mass is made in terms of gram, whereas in a FPS system it is a pound, MK system is a kilogram. Of course, in all systems, time is measured in a seconds only. But the children, to have a uniformity, the scientific community decided to use one common system, so-called SI system. In all these systems, we only can measure only three physical quantities. But whereas in a SI system, other than these three, four fundamental quantities, two supplementary fundamental quantities, total 7 plus 2, total 9 quantities are defined, 9 quantities. Okay na? So before 1960 only we used to treat these three as the fundamental quantities, but after 1960 7 plus 2 fundamental quantities are decided. Is the point clear? Fine. So what are those here? So just I'll try to show on the screen. You can see that there we have mass, length, time, temperature, electric current, amount of substance, luminous intensity, and a plane angle, solid angle. So these 7 are the fundamental quantities. 7 plus 2 are the fundamental quantities, and you also can see on the screen their units are given. It's very important. Full name of the unit and the symbol of that unit also given. So kindly just note those things are very, very important. You must know these, children. So if you want to discuss about the derived units and derived quantities, you must have an idea about the fundamental quantities and the fundamental units. Okay, fine. Now we'll try to little bit discuss about the derived units. So derived units means what? First we should take a derived physical quantities. So here let us take a few examples here. First one, let us say speed. So speed is nothing but the distance by time. Distance by time. So dear children, distance is nothing but the length, time is nothing but the second. So here speed unit is what? Meter per second. It is a derived unit. And the second one, let us say acceleration. Acceleration. So acceleration, children, speed unit and a velocity unit is the same. Don't get confused. Of course, speed might be a scalar, velocity might be a vector, but units are same for that. So acceleration is what here? Velocity by time. So for a velocity unit already we got meter per second, right? So it's the meter per second by second. It is going to be meter per second square. You also can express meter s minus 2. Okay. Third one, let us take a force. So force is equal to mass into acceleration. Mass is kg. Acceleration is here we got meter per second square. But this kg meter per second square only we can call it as a Newton. We can call it as a Newton. Okay. And one more, let us see here, work. So work is equal to force into displacement. So force is nothing but this one, right? Kg meter per second square into second. Second cancel. Is it true? So kg meter per second square. Sorry, displacement. Sorry. It's not displacement. It's a meter. So meter into meter square, right? So it is a kg meter square per second square. But this one we can call it as a joule. We can call it as a joule. Is the point clear? Fine. Next, let us see power. So here power is equal to work by time. Power is equal to work by time. So work unit is what? Kg meter square per second square by time is second only. The second square will come to the denominator. Second square into second will be second cube. So this is going to be kg meter square second cube. So this entire unit only we can call it as a watt. So dear children, so these are the few examples for actually these are the derived quantities and these are the derived units. Okay, just make a note of it. Are you able to see this? Okay, you are able to see, that's fine. Yes, dear children. So to make our measurement comfort, so to express the numbers in a comfortable manner, we are going to use the prefixes actually. So dear children, prefixes, generally these prefixes we use to express large numbers, very big numbers, at the same time very small numbers. Let me tell you, for suppose if you want to write like this 0.000001 something centimeter. So writing this again and again is not a comfort. So rather we can write 10 power minus 6 centimeters, right? So in the place of this 10 power minus 6 only, we are going to use a symbol. That only we can call it a prefix. Not only for the small number, even to express the very much big numbers also, we are going to use the concept of prefix. So usually, dear children, to express the bigger numbers, we use kilo. Kilo is nothing but 1000, that is 10 power 3 kilo. And here mega we use 10 power 6, and we use giga, that is 10 power 9. So kilo, mega, giga, tera also we can use. If you want to, we can use tera also. So tera, that is 10 power 12. So these are some prefixes which we use to express the bigger numbers. And for a smaller numbers, it is a centi. So centi is a 10 power minus 2, and here is a milli, 10 power minus 3, and here is a micro 10 power minus 6, 10 power minus 6, and here is a nano 10 power minus 9, and pico 10 power minus 12, and a few more also I can show you on the screen. You can check that. But these are the a bit important in a regular basis we use in our calculation, and the remaining also we have other than this other than this also we have a few more prefixes which I will show on the screen. Just kindly note on that. Okay, so these are the prefixes. Now dear children, let us try to see the first units of length. Let us talk about the units of physical quantities. So here we are going to talk about the first units of length. Units of length. So dear children, we know that the SI unit of length is a meter, whereas the CGS unit is centimeter. CGS unit is centimeter. That's fine. But dear children, so whenever you want to measure the very small lengths, let us say that if you want to measure the diameter of a wire, diameter of a small sphere, their meter will become very much bigger. Their meter is not useful. There we are going to use a sub-units of meter. There we are going to use a sub-units of meter. Sub-units of meter. What are those? Centimeter will be there. So 1 centimeter equal to 10 power minus 2 meter. Next millimeter is there. That is 10 power minus 3 meter. Next micron is there. Micron. So these are 10 power minus 6 meters. These are the sub-units. So if you want to use a bigger, of course, if you want to measure the distance between the two cities, meter will become very small. There we use a multiple units. There we can use a multiple units of meter we use. So there one of the important is 1 kilometer. Kilometer is equal to 1000 meters. So these are the subunits of meter and multiple units of meter. So other than these units, children, we also have a non-metric units, means scientific purpose. Whenever we are dealing with some scientific concepts, if you want to measure the what we can say size of the bacteria, or size of the atom, or size of the planets. So either these will become these all will become very big, or these all will become very small. For that only we have non-metric units. Okay, na? So now let us see a non-metric units. Non-metric units of length. Non-metric units of length. So first there we will see a bigger units. Let us see. There we can let us see a bigger units. So under non-metric units, bigger units. The first one is astronomical unit. Astronomical unit. So dear children, astronomical unit is what? It is a distance between, the average distance between the sun and earth is called astronomical unit. And how is it related to the meter is very important. So 1 astronomical unit is equal to 1.496 into 10 power 11 meters. So other than this astronomical unit, we also have a light year. We also have a light year. So by seeing this light year, some students will think that is a unit of time. No, it is wrong. Light year is a distance. Then what is the light year, dear children? So we know that light can travel 3 lakhs kilometers in 1 second. As it is traveling 3 lakhs kilometers in 1 second, can't we measure the distance traveled with the light in 1 year? We can measure. So that distance only, the distance traveled with the light through the vacuum in 1 year is called light year. Okay, so its value is 1 light year is equal to 9.46 into 10 to the power of 15 meters, or 9.46 into 10 to the power of 12 kilometers. And still if you want a bigger unit, we have parsec. Parsec. 1 parsec is equal to 3.26 light years. So these are the non-metric units of length which are used to measure the bigger lengths, very much bigger. So other than this, for example, smaller one, if you want smaller measurements. For suppose if you want to measure the what we can say radius of the atom. To measure the radius of the atom, we use a unit called angstrom. Angstrom. So dear children, 1 angstrom is equal to 10 power minus 10 meters or 10 power minus 8 centimeters. But now this angstrom became a unit, outdated unit. In the place of that, now we are using a nanometer. So dear children, 1 nanometer is equal to 10 angstroms, or 1 angstrom is equal to 0.1 nanometer. 0.1 nanometer. Okay, but if you want to measure the radius of the nucleus, this nanometer or angstrom also will become very, very big. There we are going to use a Fermi. Okay, so the second smaller unit is what? Actually Fermi. So 1 Fermi is equal to 10 to the power of minus 15 meters. So the children, this is all about the units of length, and their subunits of meter, multiple units of meter, and here non-metric units. Under non-metric units we discussed again bigger units and even smaller units. So now we see the units of mass. Children, till now we discussed about the units of length. Now we are going to see the units. We are going to see the units of mass. Units of mass. So the children, in a SI system, the unit of mass is kg, whereas the CJ system, it is a gram. So here also, the children, we have a subunits of kg, multiple units of kg, and what we can say, sorry, non-metric units of mass also we are going to discuss. Okay, fine. So now first let us see the subunits of kg. Subunits of kg. So here only we have milligram. 1 milligram. First let us say gram. So 1 gram is equal to 10 power minus 3 kg. 1 milligram is equal to 10 power minus 6 kg. Okay, so like this, 1 microgram is equal to 10 power minus 9 kg. So these are the subunits of kg. And let us say multiple units of kg. The children, when you go to any Mirchi yard or what we can cotton yard, you know, there we don't measure the quantities in terms of kg, because there very huge quantities will be there. There we use either tons or metric ton will use. Okay, so children, here quintal, sorry. So 1 quintal. So 1 quintal is equal to 100 kg. Okay, now whereas 1 metric ton is equal to 1000 kg. So these are the subunits and the multiple units. So other than this, now let us discuss about the non-metric units of mass. Non-metric units of what, children? Mass. Okay, here first let us see the bigger unit. So if you want to if you want to talk about the mass of the celestial bodies, so we take the reference, we take the mass of the sun as a reference. So what is the average mass of the sun, dear children? Yes, that only we can call as solar mass. So dear children, 1 solar mass is equal to 2 into 10 power 30 kg. 2 into 10 power 30 kg. Now let us say smaller ones. So if you want to talk about the what we can say, the mass of the subatomic particles. Mass of subatomic particles can be expressed in terms of what? AMU, atomic mass unit. So we are going to express as a atomic mass unit. This only we can write as a AMU, and still we are writing as a U. With that you should understand. Okay, so we habituated for the shortcuts, right? So U also represent AMU. A means atomic mass unit. But how to understand this atomic mass unit, children? Yes, let us take a carbon C612. And when I see even in the class also, students will ask actually, sir, why are you taking C612? Carbon means understood. Actually we have carbon isotopes also. Carbon C614 we have, but we are not good. That is a radioactive in nature. Now we are taking a neutral carbon atom, that is a C612. This carbon C612, it has some mass, right? Okay, let us say this is a mass of the C612. Now this is divided into, let us say, 12 equal parts. Try to understand. 12 equal parts. So each equal part, it has some mass, right? So mass of each part is equal to the 1 AMU. In a carbon, if you can see, there are 6 protons, 6 neutrons, and the mass of the proton is almost equal to the mass of the neutron. So now instead of talking about the 6 proton, 6 neutron in terms of mass, I can say that 12 protons are there. So 12 protons divided into 12 parts means each part is equal to the mass of proton. Each equal to the mass of proton. So its value is 1.66 into 10 to the power of minus 27 kg. Minus 27 kg. So this is all about the units of mass, their subunits of kg, multiple units of kg, non-metric units, their bigger unit and smaller unit. Now it comes to the units of time. Units of time it is. Units of time. So in all system of units, the unit of time is second only. Unit of time is second only. So what is a second day, children? So if you can take a one day, solar day, it has a 24 hours at an average. But mean solar day means one mean solar day is equal to 1 MSD. Children, MSD means not a Mahendra Singh Dhoni. It's a mean solar day. One mean solar day is equal to 86,400 seconds. So then can I write a 1 second is equal to 1 by 86,400 of MSD. That is, so 86,400th part of mean solar day is equal to the 1 second. 1 second. So other than this, we also have 1 minute. Okay, 1 minute is equal to 60 seconds, and here 1 hour is equal to 3,600 seconds. Like that, if you want a one day is equal to 24 into 60 into 60, and 1 year is equal to, so 3.16 into 10 to the power of 7 seconds. 1 year is equal to, and one what we can say, decade. 1 decade is equal to 3.16 into 10 to the power of 8 seconds, and 1 century is equal to 3.16 into 10 to the power of 9 seconds, and 1 millennium is equal to 3.16 into 10 to the power of 10 seconds. So these are the units of time. Okay, children, fine. Okay, since that time we are talking about the units, right? Okay, it might be units of length, or units of mass, or units of time, or it might be metric units or non-metric units or multiple units or sub-multiple, whatever it may be. So to write a units, children, we will follow some guidelines. So now we'll see the guidelines of units. Now let us see the guidelines to write the units. Children, whenever we are writing a units, we have a certain rules. So we must follow to write the units. It is not our wish, or it is not my wish, or it is not your wish. So we have to follow some standard rules. So dear children, in that, so let us see the first rule. Children, if you can see the units, of course, children, okay, apart from these units and all these things, we have the great persons who contributed so much to the science and technology. So just to honor, in their name, to remember their name, for a long time, I can say permanently. So we are using their name as for a physical quantities, we are using their names as a units also. So whenever we are writing the full name of the unit, first let us take out the full name. Whenever you have the full name of the unit, okay, whether it is given after scientist or not. For suppose if you can take a unit of force, unit of force, it is given as a Newton. And if you can say the unit of meter, you can say unit of length, SI unit, length, it is a meter. So if you can see, it is a scientist name, it is not a scientist name. So whether it is a scientist name or not, if you want to write the full name of the unit, first letter must be small only. Point clear? Yes. And the second one, whenever you are writing the symbol, symbol of the what we can say unit, symbol of the unit. So here you should be very careful. If it is a scientist name, so and if you want to write the symbol, then capital letter is accepted, small letter is not accepted. Okay. Whereas if you are writing the symbol of the unit and it is not after scientist, for example, length, it is a meter, right? Length, you cannot write a capital there, small letter you must use, very important. If it is a scientist name, okay, if it is given after scientist, the letter must be a capital, if not a small. Is the point clear? It is very important. And whenever you are writing the what we call the shortcut, you are taking 10 meters, the length is a 10 meters, let us say that 10 meters. Okay, now shortcut you are writing, you cannot write a 10 ms, so means here plural is not accepted. Why? This can be understood as a 2 millisecond, the complete meaning will be changed. So you cannot write a 10 ms, rather you have to write as a m only. So whenever you are writing the short units, you cannot use a plural form. Okay, fine. And here one more thing, whenever you are writing about the compound unit, see, compound unit usually it is a derived unit only. In derived quantities only, for derived quantities we have components. For example, we can say work. So for this unit is what actually formula is F into S. So we should write as a kg meter per second square into second. Means whenever you are explaining the what we can say a compound unit, so more than one unit is expressed, and definitely we write as a multiplication, right? So in that multiplication, the dot or cross or a dash also can be accepted. For example, it can be written as Newton meter, this dash is accepted, the dot is accepted as a symbol of multiplication. And even negative symbols are accepted in a compound unit. This second square, if you can say, so this is meter, sorry, this second square you can take as a take to the numerator, right? Though it can be kg meter square s minus 2. For acceleration, if you can see the unit meter per second square, so it can be written as meter into s power minus 2. Okay, fine. And here especially when we are writing the compound unit, whenever you are doing a square and a cube, all these things, students will commit some mistake. For suppose if somebody is writing 10 power 3 meter, it is a whole square is there, some students they will write like this, 10 power 3 into meter square. It is wrong. This square is applicable to this 10 power 3 also. So this can be written as 10 power 3 into 2 is 6, 10 power 6 meter square. It is accepted. Okay, now so these are the guidelines to write the units. So you should be very careful. Dear children, you might be studying 9th, 10th, 11th, 12th, as long as you have a physics, whenever you express the physical quantities, definitely will be using units, but you must be very careful. So make sure that we all are following the standards of the unit. So we have a certain rules, so we all must follow the rules to write the units. Those are only we can call the guidelines to write the units. Clear? Okay, na? So now, so dear children, so with these guidelines, we have done the concepts related to the unit A. So as I told you that in unit B, we will be talking about the measurement of length. Purely we are talking about the measurement of length. Dear children, whenever we want to measure any physical quantity, we need a device. So on what base we have to select the device is a very important. So we have to check till what small quantity it can measure, so that it can be precise, it can have more precise, very important. So smaller the measurement, smaller the value if it is measuring, means yes, it is a more capable of measuring the length accurately, of course length or mass for whatever you are using that device actually. Okay, so here, so whenever we are using any device to measure any physical quantity, the first important thing what we should understand is the least count. We have to understand about the least count. What is a least count? The children, if you can take any device, any device has certain limit. So less than that it cannot measure. If you can take a normal wall clock, see I am not talking about the digital wall clock, normal wall clock. The children, by using a normal wall clock, can we measure time in hours? Yes, we can measure. Can we measure time in minutes? Yes, we can measure. Can we measure time in seconds? Yes, we can measure. But by using the normal wall clock, can we measure the time less than 1 second? No, we cannot measure. So for that normal wall clock, children, I am not talking the digital, normal wall clock. So we can measure time up to only 1 second. So this 1 second is the least count of this wall clock. Okay. Now let us take a meter rule. Meter rule, let us take that. So by using a meter rule, of course we can measure length up to 1 meter. Yes, we can measure. Even if you can say normal meter rule, we also can measure length in inches. Yes, we can measure. Even we can measure even in terms of centimeters. Can we measure? Yes, we can measure. And can we measure length even millimeters? Yes, we also can measure. But by using a normal scale, can you measure the length less than 1 millimeter? No. So here ordinary scale, if you get a normal regular scale I am talking, so we can measure length only up to, accurately I am talking. So measuring what? Measuring also accurately up to 1 millimeter. So this millimeter is a least count. So children, for any device to have a more accuracy, least count should be very less. To have more precise, least count should be very less. Is the point clear? Fine. So with this, I think we get idea what actually least count is. The children, the smallest measurement that can be measured, that can be taken by any device is called least count of that particular device. Okay, fine. Now we'll try to focus mainly on measurement of length. Children, when I say measurement of length, yes, we can recall about the scale. The children, by using a normal scale, so till what least value we can measure? 1 millimeter. Can we measure less than that? No, we cannot measure. So least count of normal scale is 1 millimeter. But if you want to measure the length less than 1 millimeter, is this meter rule, is this normal scale is useful? No. There only we can use a vernier calipers. So the children, by using a vernier calipers, we can measure the length up to 1/10 of millimeter, that is 0.1 centimeter or 0.01 centimeter. So this is 0.1 centimeter. Okay, fine. Now if you want to measure the length less than 0.1 millimeter or 0.01 centimeter, their vernier calipers also not useful. There we are going to use one more device called screw gauge. What is that, children? Screw gauge. So by using screw gauge, we can measure the 100th part of millimeter. So this one we can call it, we can say 0.01 millimeter or 0.001 centimeter. So dear children, if you can see here, by using normal scale, we can measure distance up to what we can say 1 decimal part of centimeter. If it is vernier calipers, 2 decimals of centimeter. If it is screw gauge, 3 decimals of centimeter. Children, this only we can express like this, right? 0.001 into 10 power minus 2 meters, because 1 centimeter equal 10 power minus 2 meter, and this can be written as 10 power minus 3 into 10 power minus 2 meter. It can be written as 10 power minus 5 meter, because bases are same, power should be added. And children, this can I write like this? How? 10 into 10 power minus 1 into 10 power minus 5 meter. Yes, anyhow, this value is going to be 1. So now let us consider here. So base are same, power should be added. So it can be 10 into 10 power minus 6 meters. This 10 power minus 6 meter is nothing but micrometer. So it is a 10 micrometer. So which means what? By using this device, we can measure the length in the order of micrometers, length in the order of microns. That's what it is also called as micrometer screw gauge. Micrometer screw gauge. Okay, fine. Now let us discuss in detail about the vernier calipers, and we also can discuss about the screw gauge. Hope it's clear. So children, I think with this you hope you understood why we are calling this screw gauge as a micrometer screw gauge. Now dear children, so let us see first a principle of vernier calipers. So let me write here vernier calipers. So dear children, vernier calipers is consisting of 2 scales. One is we can call it as a main scale. One we can call it the main scale, and the second one we can call it as a vernier scale. We can call it as a vernier scale. So this main scale is nothing but normal scale only. So it is calibrated like this. It is calibrated like this. So it is, let us say, 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's like a normal scale. So this total length is centimeter, and each division is equal to 1 millimeter. So this is a normal about the main scale only. But how about a vernier scale here? How about vernier scale? Look at it. So if you want to understand that, actually first how a vernier scale is designed, further we should understand what is the principle of vernier scale, principle of vernier calipers. So principle is very important. Principle, okay. So dear children, vernier calipers is designed such a way that, very important, such a way that here n divisions of vernier scale is equal to the n minus 1 divisions, of main scale. Very important. So here n divisions of vernier scale is equal to the n minus 1 divisions of main scale. What does it mean? For suppose, dear children, for suppose here 10 divisions of vernier scale are equal to the 10 minus 1, 9 divisions of main scale. 9 divisions of main scale. Very important. 9 divisions of main scale. Then how to understand this? I'll tell you. For suppose, dear children, in 1 centimeters, how many millimeters are there? How many millimeters are there? How many millimeters are there here? 10 millimeters are there. Okay, now look at here. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 millimeters, right? 10 millimeters. Okay, now 10 millimeters. So this is fifth one. It is the 10th one. Okay, now in this, now if I cut this 1 millimeter, now this length is going to be 9 millimeters, right? 9 millimeters. Okay, now this 9 millimeters length of main scale, this we are going to divide into this from here to here. 9 millimeters going to divide into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Try to understand. Very important. 0 to 10. This is what actually the meaning of this. So the length of 9 millimeters, okay, a length on a main scale is divided into 10 equal parts. 10 equal parts. This is how actually vernier scale is designed. Okay, fine. Let us discuss in detail. Don't worry. Don't get confused. Okay, na? So first, just I told you how a main scale is divided and how a vernier scale is divided. Now it is a vernier scale. The number of divisions. How many divisions are there? 10 divisions are there. These 10 divisions are equal to the length of the 9 millimeter. So the length of 9 millimeters is divided into 10 equal parts, and it serves as a vernier scale. Is the point clear? Yes. So now, dear children, let us try to understand the least count or vernier constant, or we also can call it as a vernier constant. So how to calculate this? It can be calculated as 1 MSD minus 1 VSD. Now here you should understand what is a 1 MSD and what is a 1 VSD. 1 MSD is actually this one division. So this one division is called 1 MSD. It is equal to the 1 millimeter. Okay, now VSD means what actually? So this one is there, you know, each one is a 1 VSD. So but how to calculate this VSD? This total length is how much? 9 millimeter, right? 9 millimeter. So if you want this 1 VSD, means what? Total division is 9 millimeters is divided into 10 equal parts. So which is equal to the 0.9 millimeter. 0.9 millimeter. So here 1 MSD is 1 mm minus 1 VSD is 0.9 mm. So if you can calculate, it is 0.1 mm, or we also can write 0.01 centimeters. So this is what actually least count or Vernier constant. So what is the Vernier constant? Vernier constant is equal to the 0.1 millimeter, or in terms of centimeters means 0.01 centimeters. Is the point clear? Fine. Let us see in one more way also we can get this. Hope it is copied. Okay, now fine. So let us recall the principle of the Vernier calipers, right? So here what we wrote here, n divisions on a Vernier scale is equal to the n minus 1 divisions divisions on main scale. So if I want one division of Vernier scale, or if I want a one division of Vernier scale, and one more thing here. So let children here, let x be the one division of the main scale, that is 1 MSD, let us say 1 MSD. So x is equal to 1 MSD, that is the main scale division. So here can I write like this, n Vernier scale divisions equal to the n minus 1 into x, right? N minus 1 into x, or n minus 1 into x main scale divisions. Okay, fine. If I want one VSD, one VSD is equal to, so n minus 1 into x by n. So this is one VSD. Okay, and 1 MSD is equal to x. And here least count is what here? Least count is equal to 1 MSD minus 1 VSD. So MSD is x, VSD you can write this much, n minus 1 into x by n. Okay, now you simplify this. N is going to be the LCM, n into x, it will be xn, and you multiply with x into n, xn, x into 1, x, but this minus also is there, don't get confused. So here minus xn minus 1. Let us simplify this. Xn minus xn plus 1, plus x, plus x is there, it is the x by n here. Xn cancel. So here least count, so let me write here. So here least count is equal to x by n here. So what is the x children here? 1 MSD. What is the n? Number of Vernier scale divisions. So 1 x is equal to 1 MSD. 1 MSD is not 1 mm. So it is 1 mm by number of Vernier scale divisions 10. Also will get 0.1 mm, same we will get, or 0.01 centimeters. Is the point clear? So this is all about the Vernier calipers and its principle, and what we can say more, how to calculate the Vernier constant, how to calculate the least count, all these things. Now just let us see what actually about the Vernier calipers. So children, this is how actually Vernier calipers is going to be. Now just let us see, even I will try to show even on the screen also. So mainly dear children, if you can see Vernier calipers, so this is a main scale, so hope you all can see. So this is a main scale, okay, and it is calibrated in terms of millimeters, and this is a Vernier scale which is capable of sliding. I will try to just show you, so able to see. So this is a main scale, okay, I think you are not able to see, it's a blur it is showing, and here is a Vernier scale. So Vernier scale can slide over the main scale, dear children. And here if you can see here, see left side of this main scale, two jaws are fixed, these are called fixed jaws, and these two jaws are fixed to the a metal strip on which vernier scale is designed, so that these two jaws are able to move along with this. So these two jaws are called fixed jaws, these two jaws are called movable jaws. And the children, if you can see, these are the lower jaws, or we also can call it the outer jaws. With the help of these outer jaws, we can measure the external diameter of what we can say a sphere, or we also can measure the length. By using these two, we can say inner jaws actually. So we can measure the internal diameter of what we can say water bottle cap, something like that. And here if you can see, as I am just rotating this screw, you also can see one metal strip is coming out. This we can call the tail. With the help of this, we try to measure the depth of the things like a test tube. Okay, see, today we are not going to discuss how to measure the length and all these things, dear children. Yes, we will have one more session where purely I will discuss how to do the practical, how to measure the length and internal diameter by using a vernier calipers. In that class, in that session, we will discuss. So here purely about how vernier calipers will be there, and what are the parts and what are the uses. Is the point clear? Fine. And the children, whenever we are measuring here length or internal diameter, external diameter by using vernier calipers, yes, it is a minimum thing. Not only vernier calipers, dear children, if you want to measure any if you want to measure anything by using any device, first we must check whether is there any error or not, because if that device is error free only, it is very good to us to measure, so that we will get a correct values. Even vernier calipers also, but how to check whether error is there or not? Yes, dear children. So to measure that, first of all, these two jaws must be brought in contact. Yes, once these two jaws are brought in contact, then we have to see the vernier scale and the main scale. So dear children, and here is, for suppose here is a main scale. So in main scale it is a 0, main scale 0, 1, 2, 3, 4, 5, something like this. And even it is vernier scale, let us say that, vernier scale 0, try to understand. So now if you can see, these are coinciding like this. Yes, should coincide, try to understand. So when these two external jaws are brought in contact, such that if the 0 reading of the main scale coincides with the 0 reading of the vernier scale, then that particular vernier calipers is said to be free from 0 error. So this is no 0 error. This is actually main scale, and this is vernier scale, and this case is no 0 error. No 0 error. So dear children, if it is not coinciding only, when these two external jaws are brought in contact, but still the 0 reading of the vernier scale is not coinciding with the 0 reading of the main scale, then we can say that that particular vernier calipers has a error, so called 0 error, and we need to decide, is it a positive 0 error or a negative 0 error. So dear children, look at here. For suppose if it is not coinciding, let us say that. So it is a main scale, it is not coinciding. Okay, look at here, 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So this is a main scale. Okay, now that vernier scale is like this. So it's 0 reading something like this. So here 0 reading of the vernier scale is not coinciding with the 0 reading of the main scale. So it has some 0 error. That 0 error only we can call it as a positive 0 error. We can call it as a positive 0 error. Positive 0 error. So this much extra reading it is showing already. This much extra reading is showing actually. This much extra reading it is showing, right? So this has to be deleted. This has to be eliminated. That's what correction is negative. For positive 0 error, correction is going to be a negative. Correction is going to be negative. Okay, fine. And if it is not like a coinciding, in this case it is lying on a what is staying on a right side, right? So it also possible like this. So this is 0 reading of the main scale, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It is a main scale. So it can lie like this also. So it can be like this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay na, something like this. And look at here. Okay na. So now zero reading of the vernier scale is lying on the left side of the zero reading of the main scale. Such a error is called negative zero error. We can call it as a negative zero error, and the correction is, you can guess children, so correction is positive. Correction is positive. Correction is positive. Is the point clear? So this is all about actually errors and types. The children, when two external jaws are brought in contact, if the zero of the vernier scale is coinciding with the zero reading of the main scale, it is said to be having no zero error. If it is not coinciding only, we can say that there is a error called zero error. It can be positive zero error, it can be negative zero error. It depends on the position of the zero reading of the vernier scale. If the zero reading of the vernier scale is lying on the right side of the zero reading of the main scale, we can call it the positive zero error. If it is lying on the left side, we can call it as a negative zero error. And what is the basic formula to calculate the what we can say length by using vernier calipers? Yes, children, I am taking the case where there is no error. I am trying to understand. See, as I told you that in detail session we will have, where I will show you how to calculate the length and the diameter by using vernier calipers. In detail I will show you. Okay, fine. So the length of an object, okay, object is equal to main scale reading plus vernier scale reading into least count. So this is a formula to calculate this one. So now we are not going to any practical. As I told you that yes, we will have a special session where I will tell you how to take a MSR, how to take a VSR, if error is there how, if error is not there how, and if error is there how to correct, how to make all the corrections. I will show you in detail. Okay, fine. So this is all about the vernier calipers. It is all about the vernier calipers. Now dear children, yes, can you identify this device? Can you? Yes, I have one more device. What is this device actually? Yes, it is nothing more but actually screw gauge. Yes, it is called screw gauge. We also can call it as a micrometer screw gauge. So I told you why we are calling it as a micrometer screw gauge. That's fine, dear children. So what is the specialty of this micrometer screw gauge, dear children? Yes, its least count is 0.01 millimeter, or by using this we can measure up to 3 decimals of centimeters. It also can be written as 10 into 10 power minus 6 meters, that is 10 micrometers, or we can say it as a 10 micron. 10 micron, that's fine. So by using the screw gauge we can measure the length up to 3 decimals of centimeter. It is a more accurate. So now, so let us see first, let us see some parts. Okay, what are the parts which screw gauge has? So children, if you can see, let me tell, first of all, what is the principle of screw gauge? So children, you might be knowing about the screw and a nut. Yes, you may. Yeah, now you think, sir, we all are very familiar with the screw and nut, but why now we need to talk about the screw and nut? Hey, if you know about the screw and nut, definitely you will understand 100% about the screw gauge. Are you not believing? Yes, let us see that. So children, so we know that here is like, it is like a what we can say, some 3D type. Can we try something? Okay, it's like screw. It will be like this. It's a nut. Okay, now screw means here is a screw, right? So the screw, some threads will be there like this, not like this irregular manner. A regular manner they will be. Okay now, so just please excuse me, just I am writing like this. The children, session will go up to 1.5 hours because we are trying to cover each and every point of the chapter. These are the threads. Okay, fine. So the children, now let us try to understand. So here is a screw, here is a nut. Okay, now try to understand. So this part of the vernier calipers, we can call it sleeve cylinder. Actually, this is one cylinder type is there. This cylinder is going to serve as a nut, and here is a screw, right? Here is a screw. So in a nut, just you place a screw. Okay, if you go on rotating, so yes, that screw will move forward, right? Is moving forward. Try to understand. So here also, dear children, try to understand first. So whenever, see, for example, let us say if you make one complete rotation in a nut, try to understand. So try to understand, and as I told you that here, this part of the cylinder, this part of the screw acts, this part of the screw gauge acts as a what you can say nut, and this is going to act like a screw, right? Okay, so when we are rotating this head of the screw, when you are rotating the head of the screw, don't you think that the screw advances little bit within the nut? Yes, it can advance. Yes, it can. So for one complete rotation of the head of the screw, I repeat once, for complete rotation of the head of the screw, this screw advances some distance along its axis. This distance covered by the screw along its axis for one complete rotation of head is called pitch of the screw. Very, very important. Pitch of the screw. Very, very, very important. Pitch of the screw. So pitch of the screw is nothing but what, children, here? Distance traveled by the screw for one complete rotation of the head. One complete rotation of the head. So this one we can express P is equal to X by N. And you should try to understand. So in ideal case, the distance between the two threads, it will be equal to the 1 millimeter. Which means what? If you can rotate this head, if you can make a one complete rotation of the head, and the screw will cover the distance between the even two threads inside of the nut. Which means what here? For one complete rotation of the head, screw will cover the distance between the two threads, which is equal to the 1 mm. So pitch is equal to 1 mm. That's it. Pitch is equal to 1 mm. What is the pitch, dear children? The distance traveled by the screw along its axis for one complete rotation of head, is called pitch. So same thing, dear children. That's what I can say, that if you want to understand about the screw gauge, you must know about the screw, you must know about the nut. Because what is the principle of screw gauge? Screw in a nut. How a screw gets rotated when you are rotating, how it will advance through the nut is a concept actually. Okay, understood? Yes. Now let us see the parts of the screw gauge, dear children. So as I told you that if you can see, here is a U-shaped metal frame. For this left side of that, cylindrical solid type of object is fixed. Okay, this we can call the stud, and the right side, for me I am talking, for you it might be left side. So right side, it is cylinder is there. Okay, na? So this cylinder serves as a nut. Okay, and this one we can call a sleeve cylinder. On the sleeve cylinder only a scale is calibrated. This scale only we can call the main scale. In some textbooks it is written as a pitch scale also. It is a main scale. Usually it is calibrated in millimeters. 1 division is equal to the 1 millimeter. Okay, fine. And apart from this, yes, if you can see, here is a nut will be there, and it is covered by a metal sheet. We can call this what kind of it is a one more metal cylinder will be there here, on which one more scale is designed. Okay, I'll try to show on the screen also. So this only we can call it a circular scale, and this last part we can call it the thimble. Okay, now so these all are actually the parts of this screw gauge. So here, to make a use of it, yes, we have to fix, or we have to rotate, of course. So between this stud and this screw only, we can hold any object. If you want, any object means not a bigger one. If you want to measure the thickness of the glass plate, if you want to measure the radius of the thin wire, or a diameter of a small solid sphere, yes, those objects must be held between this screw and this a stud. Okay na? So this is all about the what we can say screw gauge and the parts. Now children, hope you understand the pitch. Okay na? Now look at here, try to understand. Let me talk about this. So here is the head of this screw, right? So if I can make a one complete rotation I'm taking complete rotation, this screw travels some distance, right? That only we can call it as a pitch of the screw. Pitch of the screw. Okay, is the point clear? Yes. Now let us try to understand. Okay, let us try to understand about the least count. Okay, so here first we spoke about the pitch. Already pitch concept is clear. So pitch is equal, let us write here the children. So pitch is equal to x by n. Yes, in ideal case it is a 0.1 millimeter in general. Okay, for a regular screw gauges it is 0.1, because for one complete rotation pitch will travel 1 millimeter, hence we will get a 0.1 millimeter. Now let us talk about the least count. Least count. Okay, if you want to understand that least count, children, as I told you that here, okay na, so here so this is called actual main scale. So here is main scale, try to understand. Here is main scale. So for this it is calibrated, as I told you that 0 1 2 3 4 5 1 2 3 4 5. So each division is equal to the 1 millimeter. Each division is equal to the 1 millimeter on head scale. Okay, and if you can see, as I am rotating, if you can see this ratchet here, the circular scale also rotating. Circular scale also rotating. Try to understand. So how many number of divisions will be there in a circular scale, dear children? In some screw gauges may be having a 50 divisions. In some screw gauges may be having 100 divisions. Some screw gauges may be having a 200 divisions also. It depends actually. It depends. But for this, the screw gauge what we have taken, it is a 100 divisions are there. So here capital N is equal to 100. So this is number of circular scale divisions. Number of circular scale divisions. Here the children, here if you look at here, okay, now okay, and here one more important point I forgot to tell you. Here there will be one horizontal axis or a line on the what actually main scale. Main scale. So this only we can call it as a baseline. This only we can call it as a baseline. This we can call it as a baseline. Okay, clear, fine. And as I told you that children, here there are a number of divisions. Let us 0. Here okay, some divisions are like this. 1 2 3 4 5 6 7 8 9, some 10 it is, and it is 1 2 3 4 5 6 7 8 9. This is a 90. Try to understand, because 90 to 0 is again 100. But here try to understand children. So when we discussed about the pitch, I told you that yes, we are rotating this head completely, I said. Okay now, but now look at here, look at here. So here each division is there, right? Each division. So here now we are not going to rotate this is a completely. So we want to move. Let us say this is 0 and this is a 99. So this is 0 children. This is 99. Try to understand. Now I'll make sure that I'm going to rotate this what we can say thimble of the screw gauge, so that circular scale also rotating, right? But I want to make now complete rotation. I will make sure that only one division will move. One division of the screw, one division of the circular scale will rotate. Right on means now the 0 is coincident with the head scale, what we can say baseline, right? Now I will rotate so that look at here. This 99 will come here and this will be 0. So means it is moved for a one division. For that one division of rotation of circular scale, okay now, here this screw will move certain distance, right? Try to understand. For this one division of rotation of circular scale, this screw will travel some distance along its axis. That only we can call it as a least count. You may get a one doubt, sir, what makes the difference between pitch and the least count of the screw gauge? Yes, dear children. So to define a pitch, dear children, here we made a one complete rotation, and in that case we have seen what is the distance traveled. But here we are not making complete rotation, we are making sure that only one division is rotated, one division of circular scale is rotated. Like if it is like a 99, if it is like it's a 0, for example 0, so one more. Now we will rotate 99 to 98, one I will rotate 98 to 97. Only one division of circular scale is rotated. For that rotation of one division of the circular scale, the distance covered by the screw only we can call it as a least count. We can call it as a least count of the screw gauge. So mathematically, how can we express the children? Yes. So least count of the screw gauge can be expressed by pitch by n. Pitch by n. For suppose in this 100 divisions are there, and pitch we got as 0.1 mm, 0.1 mm, and the number of divisions are 100. So it will be 0.01 millimeter. This is how we can calculate the least count. In exam they may ask you a question, how can we, children, to be precise, least count should be less, right? Then how can we decrease the least count? Very important, the children. So least count of the screw gauge can be decreased by decreasing the pitch or by increasing the number of circular scale divisions. By increasing the number of circular scale divisions. Is the point clear? Fine. So this is how actually we can calculate the pitch, and we also can calculate the what we can say least count. Okay, fine. And now let us see, children, as I told you that if you want to use either vernier calipers or a screw gauge or any other device, we must check whether is there an error or not. So in this case also, how to check a error is there or not? Yes, before going to check whether error is there or not, so make sure that the screw is brought in a contact. Screw is brought in a contact with the stud. Okay, make sure that yes, it is brought in a contact. In that case, look at here. Here we have two scales, right? Yes, it is a head scale, and for us the reference line is what actually baseline. Okay, now reference line is what actually for us baseline is a reference line. Try to understand. And here, children, as I told you that, okay, now here for a circular scale, zero reading will be there, right? Okay, so we brought. So this is a head scale. Okay, fine. So when you just bring a screw in a contact with the stud, if the zero reading of the circular scale coincides with the baseline, then it is said to be free from zero error. So there is no zero error. If it is not coinciding only, there is some error. So it can be positive zero error, it can be negative zero error. So look at here. So children, in this case, if it is not coinciding means it may lie above the, in the sense what, zero reading of the circular scale may lie above the index line, okay, or if it is not above the index line, obviously it must be below the index line. Look at here, it might be okay. So here zero reading of the circular scale is coinciding with the baseline, no zero error. Here zero reading of the circular scale is lying above the baseline, and it is said to be negative zero error. And for this correction is positive. Whereas if the zero reading of the circular scale is lying, it's below the baseline, is said to be having a positive zero error, and here is correction is negative. And the children, as I told you in the case of vernier calipers, yes, now we are not going to do the experiment with the screw gauge. Yes, we will have one session especially for a vernier calipers and how to measure the distance, how to measure the length, even by using a screw gauge also. Of course, we are going to have one more special session. There I will discuss in detail how to do the practical and how to measure the thickness of the thin plate and even thickness of the wire, and all these things we can. Okay, and here what is the formula to calculate the length or a diameter by using screw gauge. Yes, it is a head scale, like a main scale. This we also can call the main scale or head scale. Main scale reading plus circular scale reading into least count. So this is a general formula where there is no error. If error is there, plus or minus 0 error. Plus or minus 0 error. Depends on that. If it is a negative 0 error, it is going to plus 0 error. Plus 0 negative error. If it is positive 0 error, it is going to be negative. Okay, na? So this is about the screw gauge. And other than this, dear children, we have one more error called backlash error. Backlash error. I can say that, you know, this may occur due to the wear and tear, or sometimes, you know, due to the manufacturing defects. You know, why manufacturing defect? Until look at here. Sometimes, you know, the threads inside or on the surface of the screw will get disturbed, so that though you are rotating, for example, if I am rotating in anti-clockwise direction, the screw has to move in a proper way, right? Sometimes what happen, you know, though you will be rotating this head of the screw, but still there is no proper movement. There is no proper movement in a screw actually. So generally, if such a error is there, it's too difficult. See, it's a negative positive error, means we can correct it easily. If it is a backlash error, mostly it won't be there, ma. Of course, as I told that we use again and again. Yes, due to tear and wear, you know, wear and tear, some problems may happen. My best suggestion is that we should not use such a screw gauge. Yes, that's it. But how to avoid? Yes, to avoid this, you know, we have to rotate only in one particular direction only. You just don't go on using clockwise and anti-clockwise. Only in a particular way only. Just try to make a use of it. To avoid, I can say, but we can't make it 0. We can't make it 0. Here completely we can make it 0. So backlash error is what actually? So it happens mainly due to the wear and tear. So as you are rotating in a clockwise direction, anti-clockwise direction, there won't be any proper movement of the screw. Such error only we can call it as a backlash error. Okay, so these are the topics about actually screw gauge and vernier calipers. Fine, children. Now let us discuss about the simple pendulum. Yeah, let me show you. So first, what is a simple pendulum? What is a simple pendulum? Actually, before that, children, let us try to understand one important word here, that is a point mass. What is meant by point mass? So point mass means, some students will think that, sir, it is like a very small. It's not that. It's not like a small quantity or not that. Children, Earth, if I say Earth is a point mass, you will get surprised, sir. How can you say that Earth is a point mass, such a huge one? But when compared with the universe, yes, Earth is a point mass, our building is a point mass. When you compare with the size of the Earth, then our building is a point mass, right? Okay, fine. And whereas train, yes, train also I can say that point mass. If the train is, you know, traveling 10,000 kilometers, so the distance, when you compare with the distance covered by the train, the length of the train is very, very small only. Point mass. Try to understand. So okay, with this concept, let us try to understand the concept of simple pendulum. So here, simple pendulum is simple. Okay, simple, very simple. Okay. So it is nothing but the heavy point mass. Try to understand. So why I am saying heavy? Because it has a more weight. More weight means not more than me. Compare with the thread actually. Compare with thread. So its weight is more. So that I can say that it is a heavy one. Why I am saying point mass? Because when I take the length of 100 centimeters, compared with that length, the diameter is small. So we can say that it is a heavy point mass. So simply, simple pendulum is a heavy point mass, suspended by means of a string from a rigid support. So this arrangement only we can call it as a simple pendulum, and this is called point O, point of suspension. This is center of the gravity, and OA is a mean position. OA is called mean position. And here about the string we should learn few important things actually. So what kind of string are we going to take, dear children? Very important. So string should be massless. So when I say massless, it is a common, it is because we don't have such a thread without mass. It is highly impossible. But why we are saying massless? Compare with the mass of the bob, BOB, this heavy point mass only we can call it the bob. Compare with this, the mass of the string should be negligible. Such a mass we can call the massless. Okay, fine. And it should be of a inelastic. It should be of a massless and inelastic. Why it should be inelastic, dear children? Why it should be inelastic? So if it was elastic, this length keep on changing, right? The length of the pendulum won't be fixed. So if it is inelastic, the length is fixed. Okay, fine. And the third one, it should be of a torsionless. What if it has a torsion? It has a torsion means, it has some rotation type like this. So it will be oscillating, at the same time it is a rotating if it has a torsion. So make sure that it should not have a torsion, so that it will only oscillate. It won't rotate, it won't have any rotational motion. So such a kind of string we can call it the ideal string. Why I am called the ideal string? Because such a string won't be available. It is not at all possible at all. Okay, fine. So let us come back to this. So this is a diagrammatic representation of the simple pendulum. Yes, this is how actually simple pendulum seems to be. Children, here is a simple pendulum. So this is a bob of the pendulum. Okay, na? And with the string, and let us say this point is the point of suspension. Now let us try to understand some terms related to the simple pendulum. Dear children, this point of suspension O to center of gravity, try to understand. This length we should take, very important. So this length only we can call it as a effective length of the pendulum. Very important. O to G, very important. So effective length must be OG. Okay, na? OG. Only one gangster Pawan Kalyan movie is going to be released, right? You all are waiting for that? Yes, I'm very eagerly waiting for that movie. OG. Okay, so here OG. So O to G, this length O to G only. You should not take till here, ma. No, it's wrong. Effective length means point of suspension to the center of gravity of the bob is actually effective length. Is what actually? Effective length. Okay, effective length. That's fine. Okay. Now when this children, look at here. Now here OA is called mean position. When I take this pendulum side little bit like this, and when I just, okay, very important. This point is very important. From mean position to, now it is getting displaced. So this displacement of the bob of the pendulum from its mean position to extreme end is called amplitude. For one side, see, to make it oscillate, we have to take one side right now from, look at here. It is a mean position. Now it is displaced. So now from here to here, there is some displacement. This maximum displacement of the bob of the pendulum is called actually amplitude. So for suppose it is taken aside. Okay, look at here. So it is taken. Let us say point B, it is extreme end. So now from here to here, this, from here to here, this only we can call it as a amplitude. We can call it as a amplitude. Now dear children, okay, it is given some amplitude. Let us say that it is given some amplitude. So when it gives some, from here it is given amplitude, what happens? So it will go to this end, again come back to this. So this complete to and fro motion of the bob of the pendulum is called oscillation. Means when you take take this point B, if you leave, so it comes like this and goes here, let us say that. So it comes to this point. Yes. So let's say this point C. See, OA is called mean position. B and C called extreme ends. Extreme ends means it is going from B to A, C. Okay. A to C, again A to B. So this is a one complete, right? It's a complete, like it's a to and fro motion, complete to and fro motion of the bob of the pendulum only. We can call it as a oscillation. Look at here. If look at here, to fro, one oscillation it is. Okay, fine. Now dear children, to complete this oscillation, don't you think that it takes some time? Yes, the time taken to complete one oscillation is called time period. What is the time period? The time taken to complete one oscillation is called time period. Okay, so yes, when it is made to oscillate, of course it will be doing some oscillations. Can we calculate the number of oscillations completed in 1 second? Can we calculate it? Yes, we can calculate. That only we can call the frequency. Dear children, what is the frequency? The number of oscillations completed in a 1 second is called frequency. It is equal to the reciprocal of time period. Reciprocal of time period. So more is the time period, less number of oscillations, hence less is the frequency. Less is the time period, more number of oscillations takes place, hence more is the frequency. So these are the terms related to the terms related to the simple pendulum. Terms related to the simple pendulum. Is the concept clear? Fine. Now let us try to focus more on the time period. Okay, so how to calculate the time period, and on which factor does the time period depends, and on which factor it does not depend, and all these things also examination point of view very important. Can I erase this? Okay, fine. The children, of course, for this actually we should use a stopwatch. Hey, again I'm promising you that yes. So actually we have a practical by using the simple pendulum, how to calculate the acceleration due to gravity in a given place actually. Yes. So children, 3 practicals we have. One is vernier calipers, screw gauge, third one is simple pendulum. Yes, we will try to have a special sessions where we will be doing a practical by using vernier calipers, screw gauge and a simple pendulum. For today, try to understand the concepts. Okay, fine. So actually what we should do, and the children, first, okay, look at here. So how to calculate time period, let us take a simple pendulum. Okay, for example, a simple pendulum taken aside, one extreme end, point C, and when just leave it, what happens? It passes through the main position and it will go to the another extreme end B. It will come here. So this only we can call it a one complete oscillation. For this, the time taken only we can call it time period. But the children, what we are going to do, first we will fix a length of the, effective length I told you, from this point of suspension to the center of the bob. So length can be, we can try 40 centimeters, 50 centimeters, 60 centimeters, 70, different lengths we will try. First let us say that here length we have taken a 40 centimeters. Example. And the time taken for one complete oscillation is called time period. But for one complete oscillation, when you try to calculate, the accuracy may be missing actually. To avoid that, means error might be there. To avoid error, I can say that to minimize the error, dear children. So instead of one oscillation, we can take a time taken for 10 oscillations or 20 oscillations, up to you. You may get one out. Sir, if you want to calculate time period, we should take for one oscillation, right? Why are you taking for 20 oscillations? Let me tell you. So for suppose, dear children, so initially it is there here at this point only. It is left. We have to count here to here 1 oscillation, 2 oscillation, 3, 4, 5, 6, like this, 19, 20 oscillations. Yes, for the 20 oscillations we should calculate time. Let us say small t we got actually the time taken for 20 oscillations. 20 oscillations. For example, let us say that it got some 40 seconds we got. Example I'm telling you. This is time taken for 20 oscillations. 20 oscillations. Time taken for 20 oscillations. But I want the time taken for one oscillation, right? What I should do if I want to get a one oscillation? Divide with the 20. Divide with the 20. This is a time period. That's it. So small t is a time taken for 20 oscillations. If you divide that with the 20, you will get the time taken for one oscillation. That is going to be time period. So this is our idea. So for this, we can minimize the error. We can minimize the error. So like this, yes. For a L value, for L is equal to 40 centimeters, you will get a T value. Again try with the 50 centimeters, we will get time period. With the 60 centimeters, calculate time period. So like this, for different lengths of the simple pendulum, try to calculate the time periods taken. So finally, we get a list of length of the pendulum. For a different length of the pendulum, we get a different time period, right? So let us say that serial number we get effective length, and small t, okay na, that we calculate for. Then from this capital T, how we'll get here? Small t by 20. Okay, then let us calculate a t square, then L by t square. Then you may get a one doubt, sir, why we need a L by t square value? Okay, this is a tabular form actually we'll get. So of course, when we do practical, we need this, but now it is not required. Just try to have idea about this actually. And for a L value and a t square value, we must make a graph. Okay, so here is L is taken on x-axis, t square is taken y-axis. We get a graph like this, straight line, but not passing through the origin. You may get a one doubt, sir, why it is not passing through the origin? Of course, it will pass through origin, but L must be 0. But is it possible to have a simple pendulum with a effective length 0? It is not possible. So it won't pass through this. Okay, fine. And by using this graph, dear children, of course, what is the slope of this graph? Slope of y component by x component. In the simple terms, I'm telling you. So slope of L t square graph, it is going to be a t square by L. Now, why this is important? You may get a one doubt. Yes, I'll tell you. This concept is important. Please remember this. Last we'll be using this. So this t square by L value. So from this graph, can we calculate t square by L? Yes. By using this slope only, we are going to calculate the acceleration due to gravity. You may get a one doubt, sir. How can we calculate the acceleration due to gravity by using this one? Yes, we will calculate. We will calculate. Just wait. Okay, na? So this is about how to calculate the time period of the simple pendulum and the L versus t square graph and the slope of the graph. Now, dear children, let us see the factors affecting the time period. Factors affecting the time period. So here, factors, very important. Factors affecting the time period. Factors affecting time. Children, experimentally it has been proved that time period of a simple pendulum, okay na, depends on effective length. So experimentally it has been proved that time period is proportional to the square root of the length. Dear children, if two pendulums with two different lengths are given, so to compare their time periods, we can write T1 by T2 is equal to square root of L1 by L2. Square root of L1 by L2. And the second factor is acceleration due to gravity. Acceleration due to gravity. Acceleration due to gravity. So experimentally it has been found that time period of a simple pendulum is inversely proportional to the square root of the acceleration due to gravity. To compare if two simple pendulums are taken to the two different planets, then to compare the time periods, T1 by T2 is equal to square root of G2 by G1. Square root of G2 by G1. So let us say it is the equation 1. Here is the equation 2. Equation 1, equation 2. So the children, from that equation 1 and 2, I can write like this. We can write, square root of L by G. So whenever there is a proportional symbol, it can be replaced by a constant, right? So called proportionality constant. T is equal to K into square root of L by G. So later this K value experimentally has been proved as a 2 pi. Okay, now let us substitute in this. So it is T is equal to 2 pi into square root of L by G. So children, this is a final expression to calculate the time period of a given simple pendulum. If you know the length of the pendulum and if you know the G value of that particular place, then you can substitute, you will get a T value. Okay. And did you remember? I said that by using a simple pendulum experiment, we can calculate the acceleration due to gravity. How? Yes, look at it from here only. Did you square on both sides? If you can square on both sides, T square is equal to 4 pi square L by G. So get this G this side, T square this side. So G is equal to 4 pi square into L by T square. This can I write like this? Can I write like this? G is equal to 4 pi square by T square by L. T square by L. Look at here. T square by L. Yes, just let us recall. Before here I wrote something. Yes, T square by L value. How to calculate from that T square L graph is there here. It is nothing the slope of the LT square graph. Children, 4 values, 4 only. Pi is 22/7. And this T square by L, slope of LT square graph, this we can calculate from that graph, right? So by substituting this slope value, pi value, we calculate the G value. That is actually our idea. Okay, now fine. So these are the factors affecting. Hope it is copied. Copied. Yes. Now let us see the factors on which pendulum, what we can say, time period does not depend. Time period does not depend on, very important. First one, amplitude. It does not depend on amplitude. But at the same time, so by saying it does not depend on amplitude, for example, it is a mean position. From here to here, yes, we can give this much amplitude. Because sir, anyhow you said that it doesn't depend on amplitude. Let me take from here to here. And if I leave, no, because it won't do proper oscillations. It won't do proper. Of course, it does not depend on amplitude. At the same time, it should not exceed 5 degrees. It should not exceed 5 degrees. You cannot take here and you cannot make it to oscillate. Oscillation will get disturbed and you won't get a time period. Okay, now fine. And the next one, shape and size. Shape, size, color even. Color of the bob of the pendulum doesn't matter. And the very important is weight also. So weight of the bob of the pendulum also doesn't affect the time period. Because I said that weight doesn't depend, you cannot take a 3 kg, 4 kg, 5 kg weight actually. In that case, we cannot make it oscillate also, the thread will get disturbed because we are taking such a ideal string we are taking actually. Slight difference, weight means slight difference, it won't get affected. Okay, na? Fine. So here is a last concept of the session. So when I say last concept of the session, the students who are watching this video continuously, they feel, thank God sir, we are going to complete our entire session. Yes, we are going to complete. So the last one is what actually? Seconds pendulum. It is what actually? Seconds pendulum. So dear children, what is the seconds pendulum? Look at here. So for suppose here is this one. It is from here. Experiment. Here. Complete one oscillation, right? Now, for example, for this 2 motion, 1 second it took. Means what the total time taken for oscillation? 2 seconds. 1 second, 1 second, 1 second, 1 second, 1 second, 1 second. So the time period is how much? 2 seconds, right? For a 2 motion, 1 second, fro motion, 1 second. So the time taken is 2 seconds. The pendulum whose time period is 2 seconds, or else the pendulum which takes 2 seconds to complete one oscillation is called seconds pendulum. So time period is how much? 2 seconds. Then very important. Then what is the frequency of the seconds pendulum? Children, we know that frequency is equal to 1 by time period, that is 1 by 2. So frequency is equal to 0.5 hertz. 0.5 hertz. Dear children, if you can substitute t is equal to 2 seconds in this formula, t is equal to 2 pi into square root of L by G. So substitute G value and t is equal to 2 seconds and we'll get L value, right? Yes. So we get L as 1 meter, that is 100 centimeters. Dear children, these 3 points are very important regarding the seconds pendulum. The pendulum which takes 2 seconds to complete one oscillation is called seconds pendulum. So the time period of a seconds pendulum is 2 seconds. The frequency of the seconds pendulum is 0.5 hertz and the effective length of the seconds pendulum is 100 centimeters. Okay, dear children. So with this maximum concepts we covered actually. Even numericals also uploaded. Kindly check the playlist. Dear children, already this chapter was uploaded, like it's a topic was it was uploaded. Kindly check the playlist. Even I'll try to give links in the description where even numericals also covered. And even some students are requesting us to, sir, even discuss the theory questions also, exercise based theory question. Yes, we'll try to just upload the exercise theory based, we'll try to discuss I may not write each and everything on a board. Okay, no? So each and every question I'll try to discuss. For that also we'll try to have one session. Okay, dear children, so with this we have completed one short video of measurements and experimentation. So thank you so much for all the patience and all the support. Okay, dear children, thank you so much. All the very best.